Every single day, every single hour, for billions of years, thick droplets condense in the cloud layers 60 kilometers above the surface, grow heavy with sulfuric acid, and begin to fall. They fall for kilometer after kilometer through the thick amber sky. Then, at around 47 kilometers altitude, the temperature spikes past 300 degrees Celsius. The droplets evaporate. They rise back into cloud. They condense again. They fall again. They evaporate again. The rain on Venus has never, not once in its entire geological history, reached the ground. Not the surface temperature of 465 degrees. Not the atmospheric pressure 92 times greater than Earth's, the equivalent of being a kilometer underwater. Not the fact that a day on Venus lasts longer than its entire year. It is the rain that breaks something open, because rain to us is a promise. Rain is what a living world does, and Venus has been keeping that promise in the clouds and breaking it before it arrives, forever. This is the story of how a planet almost identical to ours, same size, same age, same raw materials, turned itself into the most hostile surface in the solar system. And it is the story of why that should matter to every single person alive on Earth today. 4.5 billion years ago, the solar system was a spinning disk of gas and dust. Out of that chaos, gravity gathered rock into planets. Venus formed 108 million kilometers from the Sun. Earth formed 150 million kilometers out. They were, in nearly every measurable way, twins. Same bulk composition, same geological architecture, same starting inventory of water, carbon, and nitrogen. If you had looked at the two planets side by side in those first 100 million years, you would have struggled to predict which one would become a paradise and which one would become a furnace. NASA climate models now tell us something extraordinary. Venus may have supported liquid water oceans for up to 2 billion years. Let that number land. 2 billion years. Complex animal life on Earth is only about 600 million years old. The Venusian Ocean, if it existed, lasted more than 3 times longer than every fish, insect, dinosaur, and mammal that has ever lived on our planet. It was an ancient world by any standard. And it was, at least potentially, alive. In 2016, scientist Michael Way and his team at NASA's Goddard Institute for Space Studies built a virtual ancient Venus. They gave it a shallow ocean, a nitrogen-rich atmosphere, and the same sluggish 243-day rotation the planet has today. Then they ran the simulation forward through simulated millennia. What they found was not what anyone expected. Venus's slow spin was not a death sentence, it was a shield. Because the planet rotates so slowly, its sunlit face bakes under direct light for almost 2 Earth months at a stretch. That relentless heating causes moisture to rise and form a permanent dense cloud deck over the dayside hemisphere, a reflective barrier that bounces a significant fraction of the sun's energy back to space before the planet can absorb it. In the model, this mechanism was powerful enough to keep the surface temperatures mild, despite Venus being closer to the sun than Earth. The ancient planet may have been warm, cloudy, and persistently damp, more like a tropical greenhouse than an inferno. We know Venus had water not just from computer models, but from a chemical fingerprint it left in its own atmosphere, one that cannot be explained any other way. Water molecules come in 2 varieties. Regular water, 2 hydrogen atoms bonded to 1 oxygen, and heavy water, where one of the hydrogen atoms is replaced by deuterium, a heavier isotope. On Earth, the ratio of heavy water to regular water sits at a known stable value. On Venus, that ratio is more than 150 times higher than on Earth. The explanation is stark. Light hydrogen is easier for ultraviolet radiation to strip away from water molecules in the upper atmosphere and send bleeding into space. Over billions of years, the ordinary hydrogen fled. The heavy hydrogen stayed. And what remains is the ghost of an ocean, a ratio pressed into the atmosphere like the chemical outline of something enormous that is no longer there. Venus's atmosphere is carrying the memory of water it lost. The water itself is gone, but the planet cannot stop telling us it was there. So, how does a world with 2 billion years of ocean become this? How does a planet cross from temperate to catastrophic? The answer lies in a feedback loop so elegant and so merciless that once it begins, nothing in the known universe has ever been shown to stop it. Warm a planet. The warmth causes water to evaporate from the surface. Water vapor enters the atmosphere. And here is the critical thing. Water vapor is itself a greenhouse gas, a potent one, far more powerful molecule for molecule than carbon dioxide. More water vapor means the atmosphere traps more heat. More heat means more evaporation. More evaporation means more water vapor. The loop tightens. There is no equilibrium to reach, no natural thermostat that cuts in and says, enough. In 1969, Caltech physicist Andrew Ingersoll published a paper with a title that reads like an epitaph. The Runaway Greenhouse, A History of Water on Venus. He described what is now called the Simpson-Nakajima limit, the point at which a planet's atmosphere can no longer radiate away heat as fast as it absorbs it. Below the limit, a planet can cool itself. Above it, the surface temperature does not stabilize. It climbs, and keeps climbing, until the oceans are gone. On Earth, we have a safety valve. Rain dissolves carbon dioxide, forms weak carbonic acid, weathers silicate rock, and carries carbon into the sea, where it sinks and is eventually pulled back into the mantle by plate tectonics. The carbonate-silicate cycle. It is one of the great unsung mechanisms keeping this planet alive. It requires two things: rain that reaches the ground and a planet with moving tectonic plates. Venus lost both. Once Venus's oceans began to evaporate, the rain grew shallower. The carbonate-silicate cycle slowed. Without water to lubricate the rock, the crust may have stiffened into a single immobile shell, ending plate tectonics altogether. Volcanoes continued erupting, pumping carbon dioxide into the air. But without rain and without subduction, nothing drew it back down. The gas accumulated in the atmosphere, year by geological year, century by century, thickening the thermal blanket, deepening the trap. And the pressure. This is something that gets overlooked. Venus's atmosphere is so dense that its sheer weight compresses the air near the surface. Compressed gas is hot gas. Even if you removed every molecule of carbon dioxide from Venus's atmosphere and replaced it with nitrogen, the surface temperature would still be several hundred degrees from pressure alone. Venus built a pressure cooker on top of an oven. The combination was lethal beyond any single mechanism. But what broke the balance in the first place? What pushed an otherwise cloud-shielded, ocean-bearing world past the point of no return? Here, the story descends into fire. In 2022, Michael Way and his colleagues published an analysis of Venus's volcanic history that reframed the entire question of how the planet died. Their conclusion? Between roughly 250 million and 3 billion years ago, Venus experienced eruptions on a scale that has no parallel in Earth's geological record. What geologists call large igneous provinces, the same category of event that produced the Siberian traps, the eruption that annihilated 96% of marine species 252 million years ago, were happening on Venus repeatedly, stacked on top of each other, faster than the planet could recover. Multiple flood basalt events in rapid succession, each one saturating the atmosphere with carbon dioxide and sulfur gases before the previous eruption's damage had cleared. On Earth, the Siberian traps killed nearly everything alive. On Venus, the equivalent events may have killed the planet itself. The Magellan spacecraft confirmed what this volcanic history left behind. Launched from the payload bay of Space Shuttle Atlantis on May 4, 1989, Magellan spent 4 years mapping Venus with the synthetic aperture radar, radio waves that pierce cloud cover and bounce off terrain with photographic precision. What it revealed was a world almost entirely paved in volcanic rock. At least 85% of Venus's surface is covered in lava flows, thousands of shield volcanoes. Vast plains of solidified basalt stretching to the horizon, and hundreds of strange circular features called coronae. Blobs of molten rock that rose from the mantle domed the crust upward like a blister, then collapsed back inward, leaving enormous rings pressed into the stone. In 2023, scientists re-examined archival Magellan radar images of a region near the Venusian equator called Atla Regio, home to two of the planet's largest volcanoes, Ozymandias and Maatmons. Between two radar passes taken just 8 months apart in 1991, a volcanic vent near Maatmons had visibly changed shape. It had enlarged. Lava had flowed from it. Venus was not merely a museum of ancient catastrophe. Venus was still erupting. The fires that killed it are still burning. We have seen the surface of Venus exactly once, and it nearly cost the machines that looked at it everything they had. On March 1st, 1982, a Soviet spacecraft called Venera 13 hit the Venusian atmosphere at hypersonic speed and began its fall toward the surface. It deployed a parachute at 47 kilometers altitude, then, as the thickening air slowed it enough, released the parachute and rode the last distance down, on drag alone, through clouds of concentrated sulfuric acid, through temperatures climbing past 200, 300, 400 degrees. It touched down at 0357 UTC on a basaltic plain just east of the highland region called Phoebe Regio. The Venera 13 lander was 760 kilograms of titanium and steel, hermetically sealed. Its interior maintained at 30 degrees Celsius and near Earth pressure, even as the outside temperature reached 457 degrees, and the atmosphere pressed inward at 89 Earth atmospheres. It was designed to survive 32 minutes. It lasted 127, nearly 4 times its design life. In that time, it drilled a core sample from the bedrock beneath it, analyzed the chemistry of the rock, and transmitted to the relay satellite overhead the first color photographs ever taken on the surface of another planet. The images showed flat, angular slabs of dark stone under a sky the color of old bronze. Blue wavelengths of light are absorbed by Venus's thick atmosphere. Everything on the surface is bathed in amber. The rocks were sharp-edged and unweathered, because without water, erosion on Venus is almost impossibly slow. Geological features can persist for hundreds of millions of years without wearing down. The landscape Venera 13 photographed may look almost identical to how it looked when the last Venusian ocean evaporated. The last images ever captured on the surface of Venus were transmitted by Venera 14 4 days later, on March 5, 1982. No lander has touched Venus's surface since. 43 years have passed. Those 127 minutes of Venera 13's operational life remain the entire visual record humanity possesses of another planet's ground. We have been living off that single morning's work ever since. Out comes the question that every scientist who studies Venus is careful about answering, because the answer is more nuanced than either the alarmists or the dismissers want it to be. Could Earth become Venus? Could we, by continuing to burn fossil fuels and thicken our own carbon dioxide blanket, trigger a runaway greenhouse on Earth? The measured answer, based on the current evidence, not from human emissions alone. Earth is buffered in ways Venus no longer is. Our atmosphere is dominated by nitrogen, not carbon dioxide. We have living oceans actively absorbing carbon. We have plate tectonics still running the carbonate-silicate cycle. A 2013 analysis estimated that triggering a true runaway greenhouse on Earth would require roughly 10 times more carbon dioxide than exists in every coal seam, oil reservoir, and gas pocket in Earth's crust combined. A true Venus-style collapse is not our near-term fate. Venus did not have to reach 465 degrees to destroy itself. Every degree of warming that evaporated its oceans a little further, every century of volcanic carbon dioxide that accumulated without removal, every decade that passed without rain completing its fall, each was a step down a staircase that only went one direction. You do not need to reach Venusian temperatures to collapse a civilization. You need only to cross the thresholds that matter for human life, for sea level, for monsoon patterns, for the agricultural calendars that 10,000 years of settlement were built around. The runaway does not have to be total to be catastrophic, and there is a longer view. In approximately 2 billion years, the sun will have brightened enough that Earth will cross its own Simpson-Nakajima limit. The oceans will evaporate. The carbon cycle will fail. The rain will stop reaching the ground. Earth will become Venus. Not because of anything we did, but because the physics that governs every rocky planet near a brightening star is the same physics, and it does not negotiate. We are not near that edge today, but Venus shows us, in perfect geological detail, what that edge looks like from the other side. We are, finally, going back. After more than 4 decades of silence, 3 major missions are now in development to return to Venus. And what they are looking for, at their deepest level, is the moment. NASA's Veritas mission will carry synthetic aperture radar capable of producing 3-dimensional global maps of Venus at resolutions that make Magellan's imagery look like a pencil sketch. It will measure gravitational anomalies to map the planet's interior structure. It will carry a near-infrared spectrometer that can read the chemical composition of the surface directly, distinguishing ancient from recent volcanic rock, forensically dating the eruptions that may have tipped the climate. The Da Vinci mission will send a spherical probe, 1 meter across, built like an armored ball, plunging through Venus's atmosphere, sampling its chemistry at every altitude as it falls. It will descend for over an hour before impact, photographing the surface and measuring gas concentrations in an atmosphere that has not been chemically profiled in this detail since the Soviet Venera program ended in 1985. The European Space Agency's Envision mission will map Venus in radio wavelengths sensitive enough to detect differences in surface rock composition across the entire planet. A forensic survey from orbit, traveling at 35,000 kilometers per hour, reading the geological record of a 4 billion-year catastrophe. What all 3 missions share is a single question underneath all the others. Where, exactly, is the line? Where in Venus's geological record does the temperate world end and the inferno begin? If we can find that boundary in the rock, date it, characterize it, understand precisely what conditions crossed it, then we will know, with a precision no climate model alone can give us, how thin the margin is between a living planet and a dead one. There is a thought experiment that planetary scientists sometimes allow themselves, usually late in a conference when the data is done and the conversation goes somewhere quieter. If you stood on the shore of Venus's last ocean 2 billion years ago, what would you have seen? A sky perpetually thick with cloud because the slow rotation ensured moisture never fully dispersed. A light that was dim and diffuse, not Earth's sharp blue clarity, but something more like an overcast afternoon that never ended. The sun a pale smear behind white. The air would have been warm, the ocean shallow, tropical. At your feet, dark basaltic rock, fine-grained and volcanic, the same mineral that Venera 13 drilled through with a titanium bit in 127 minutes of borrowed time. The ocean was real, the shore existed, and then the volcanoes came, not once, but again and again, faster than the planet could recover. And the feedback ceased, and the rain began its eternal, incomplete journey, forming, falling, evaporating, rising, forming again, never landing again. The last Venusian ocean did not end in a single catastrophe. It went the way all losses go, gradually, then suddenly, shallower by increments, salt concentrating in the remaining pools, the chemistry of the surface rock changing as the carbon cycle failed. A world that had known water for 2 billion years, learning for the first time what it meant to be dry. We study Venus because it is the only place in the known universe where we can see, in full geological clarity, what the end of an Earth-like world looks like. Not from an asteroid strike, not from a dying sun, from a planet undone by its own atmosphere, by the same physics that operates on our world, at smaller magnitudes for now. The bronze-lit rocks photographed by Venera 13 on the morning of March 1, 1982, are still there, unchanged because nothing on Venus changes anymore. The rain still forms in the clouds above them, still swells, still falls, still vanishes into heat 47 kilometers above the ground. The distance between our world and that one is 38 million kilometers at its closest, a heartbeat of astronomical distance. The distance between our atmosphere and that one is a matter of chemistry and feedback and time. And the distance between a planet that keeps its ocean and a planet that loses it is the distance between everything that has ever lived, and 465 degrees of perfect, permanent silence.